you. Thank you, Amy, for the great introduction. So today I'm going to be presenting on a scalable multi-probe system for simultaneous neuropixel recordings across multiple cortical regions in non-human primates. Quite a mouthful of a title, but to start things off, wow. Okay. So in humans, complex motor and cognitive skills are fundamental to everyday life, whether it is drinking from a soda can or choosing an app on a tablet. All of these require coordination from multiple regions in the brain. So, for example, in complex reaching tasks, such as what is studied in the Erzburn lab, two different areas, premotor cortex and primary motor cortex, help coordinate that, with premotor cortex, shown in red, traditionally thought to be the planning phase, and primary motor cortex traditionally having the execution part of a reach. But these are two sort of fundamentally different parts of the brain. And it's some sort of coordination between those two regions. However, these two regions and other unknown, maybe associated regions may not be spatially near each other, and it could span a large number of neurons. So there's a need to develop models and methods of collecting data from large regions of the brain at the same time so that we can compare these two data streams and see how these different regions are coordinating. Within the field of neuroscience, there's well-established models for studying this. So rats and non-human primates are the most common models and have been used in a number of publications. However, methods are sort of more variable, and there's no one-size-fits-all method. But for studying within models, sort of these distributed circuits, we can evaluate methods sort of in three broad categories and compare them to each other. So the first category is broad coverage. How much can it actually record from spatially and number of neurons? The next is flexible targeting. Are you able to hit different brain regions, or is it just sort of one region at a time? And between experiments, you can only record from wherever you implanted. And the last thing we can compare is precision. How precise are the signals? Are you able to distinguish single units from each other, or are they more averaged across each other? And of course, the best method would be right in the center of balancing all three of these different properties. So some popular methods of collecting data are first ECOG, which is some electrodes placed directly on exposed surfaces of brain. They lean more towards just broad coverage. They can get a lot of data at once. They have some precision, but they can't really distinguish sort of individual neurons from each other. And it's more difficult to flexibly target different regions of the brain day to day. Utah arrays are another common modality of recording, which are a rigid microneedle array that's inserted into the brain. This has more precision than the ECOG arrays, but still has some of that broad coverage, but it's less difficult to flexibly move them around between sessions. However, one sort of more emerging technology is neuropixels, which allows for this flexible targeting and has good precision. So with some modifications, I hope to bring it closer to the center with some broad coverage. So what are neuropixels? Neuropixels are these ultra-thin needle-like probes that are designed to simultaneously record from hundreds to thousands of neurons. And they allow for deeper targeting of brain regions than many conventional probes. So, for example, compared to ECOG, you can more clearly get closer to deeper brain structures than something that's just on the surface of the brain. In many mouse studies, they have been very popular, as combining multiple of them allows for that broad coverage that we are seeking. And they have a number of great properties to them. So, for example, the one sort of on the left there is a whole bunch of micro manipulators that can move all around the rat and record from a whole bunch of different locations. And there have been upwards of 4 to 6 to 8 probes inserted at once and allow for a bunch of data collected. However, rats are not as good of a model for human characteristics as non-human primates are, as they have much less complex brains, and it is not easy to translate technologies developed off of a mouse model to humans. However, within non-human primates, there is much less development in the field of multiple neuropixels in the brain at once. Those that do exist are very rigid. They can only really target one region at a time that's very narrow, maybe about 5 millimeters. And they can't be moved around within that 5 millimeters. Wherever they are placed, that's where they can record. And that's not very useful to experimenters. It's more useful to be able to, oh, well, today I want to move 2 millimeters to the right, but you can't do that with these designs. Additionally, they are such narrow designs and such inflexible designs, they do not allow the integration of additional techniques with neuropixels. So neuropixels are great for getting that raw data, but they don't establish sort of any causality. However, by combining with things such as optogenetics, which is sort of a viral injection placed into the brain that allows us to manipulate how neurons fire with light, we can better establish more causality with our recordings. But existing designs don't leave any space for this addition of optogenetics or the addition of any other recording techniques. So to address this, I created a checklist for some design needs for a complete non-human primate multi-probe system. So the first is, of course, broad cortical access. So you want to be able to get a whole bunch of data all at once. And sort of adjacent to that, you need to have sort of that simultaneous multi-probe recording. So having more than 2 probes at once, or more than one in general. And session to session repositionability. So being able to go in one region for one recording session and then being able to maybe go somewhere adjacent to explore what's right next to where you recorded to create more of a 3D model of the brain. And finally, allowing built-in optical stimulation or multimodal integration in general, rather than it being an afterthought and there being no room for it. So the aims of this thesis were first, aim 1, to develop and validate a new multi-neuropixel fixture to address what a complete non-human primate multi-probe system needs. And the second was to quantify and predict neuropixel probe trajectories with these new fixtures. So basic components of any design placed on a non-human primate can be broken down into 2 parts. The first is the chamber. The chamber is what attaches to the primate and allows access to the brain. And the second half is the actual fixture, what holds the neuropixels, what advances them into the brain. And fixtures attach, of course, to chambers and create the whole recording system. Within the Osborne lab, we have sort of a established chamber design that is used across animals and across different designs of fixtures. So the basic concept is that, of course, before surgery, you have just the skull, the dura, and the brain. But after surgery, there's now a cranial window that allows you to access the brain with an artificial dura and a chamber that you can attach to. The chamber is about 20 millimeters wide, and then everything can go within that 20 millimeters, including grids. So this 20 millimeter design is much larger than most other existing cranial windows in the literature. Traditionally, they tend to do just burr holes, which really leaves only room for maybe like 1 or 2 neuropixels to go through at once. This chamber is much larger than other protocols. part of this chamber, there is a removable grid. So within the brain, there's actually a pulse, and that pulse, and that will cause artifacts within your data. So as you have maybe a rigid little electrode within the brain, as your brain jiggles around it, you're going to get a whole bunch of extra noise. By placing a flat sort of grid over the top, you can apply gentle pressure and keep the brain from jiggling as much. And by having labeled sort of metadata to your collected data and coordinate sort of where on the surface you recorded from to whatever data you got. And a number of different designs have been developed in the lab, whether it's sort of this new grids or individual holes that are numbered. Onto the fixtures themselves. In the past, there was a first generation fixture that was designed. This held a single neuropixel within the chamber, along with an optic fiber that could be placed anywhere relative to the neuropixel probe. The probe was attached to a hydraulic micromanipulator that allowed movement in X, Y, and Z. So there's two sort of little lead screws at the bottom that allow for X, Y, which allows you to move around within your chamber and target a whole bunch of different regions. Within Z, there's two different speeds that can be moved in. There's both the coarse drive and the fine drive. The coarse drive is more mechanically, so you have to twist it with your fingers and move it, and it causes a lot of wobbling, but that allows you to get the probe really close to the surface of the brain. And then by using the fine drive, which is oil hydraulically moved, you can then insert the probe into the brain very steadily and try and get as perpendicular into the brain as possible. This also helps reduce the chance of probes breaking. Evaluating how this design performed against that checklist we established earlier, it has broad cortical access. You can get a whole bunch of data at once. There's good repositionability between sessions. So upwards of 10 millimeters can be hit by going sort of to the extremes of the chamber. Additionally, there's multimodal integration. So there was proven optic stimulation results where by placing a fiber close to where we were recording, we got good response from the neurons. However, inherently, since it's just a single probe, you can only record with one probe, and that limits how much data you can actually have. In addition to that, it limits how much data sort of spatially you can get at once. So to try and combat that single probe limitation of the first generation, a second generation design was created. So the thought was, well, it was so successful to use this drive that moves in X, Y, and Z. What if we just put two of them? Two probes, each on their own drive. Each drive could, in theory, move independent of the other and allow for a bunch of different combinations of probes within the chamber. However, when evaluating this old design, the broad cortical access was really limited. It only hit about 5 millimeters compared to the 10 millimeters of the first generation. This was largely due to having two different drives. They started hitting in the middle. So you could only really hit sort of edge cases. And the angle at which those edge cases were occurring, you couldn't go all the way to the edge of the chamber. Simultaneous recording, despite there being two probes and allowing two probes worth of data, there was some occasional noise between the probes. So since there was no barrier between the probes, any cables that flopped over were able to interact with each other. And there was unexplained noise when looking at sort of what frequencies probes were correlated at. However, it still kept some of the benefits of the first generation. So the drives still allowed for easy repositionability. They were able to move around somewhat independent of each other, and there was still built-in room for optic fibers. So from these early designs, there was a number of things that were learned. So having multiple independent drives was a no-go. Not only did it limit the reachable area within the chamber, it also was quite heavy on the animal. And of course, there was the contact between different cables during recordings. So there has to be something, a physical barrier between the probes that reduces this chance of cables coming in contact with each other. And finally, 2 simultaneous probes may be insufficient to actually capture the distributed activity. So the more the merrier. In order to address that, I created the 3rd generation design. So the goals were to expand the benefits and reduce the losses of the first 2 generations. I cut down the number of probes from the 2nd generation to a single probe, which had worked well, and attached a fixture that could hold upwards of 3 different probes on at once. These 3 different probes had built-in physical barriers between them. So as you can see, there's one half that holds a single probe and it has no contact with any other probes outside of it. And then the second half with 2 probes over here has a barrier where the probes are sort of back to back to each other. This fixture is then screwed together so that 3 probes can be held at once, and it is put onto a single drive. The single drive has the benefits of the 1st generation, so it has that maneuverability within the chamber without having to worry about hitting into a 2nd drive. And finally, there is an additional physical barrier on top to keep all the cables in place, sort of increase cable management and really decrease the risk of anything hitting each other. When evaluating this design, we have the easy repositionability. There's that drive that moves in XYZ, so that's a check mark. Then, before ever implanting it into the animal and seeing that noise that we had seen before, I wanted to evaluate how it would perform outside of the animal to address maybe any issues. To do this, I did a saline test. So the saline test allows us to inject artificial signals and compare how the probes work relative to each other. To ensure that we were testing for crosstalk, I put probes in 2 separate saline beakers, where one beaker got signal and the other beaker had been grounded, where the thought is that only the probe that is placed in the beaker with signal should be seeing any signal. And if the probe that is placed in the grounded beaker sees any signal, then we are getting crosstalk. But if it doesn't, it should be good, and it should just have sort of a static signal of just the ground. When looking at how it performed in there, it did very well. The only places there was any noise was at 60 hertz, which was likely due to all the electronic devices in the room that it was being tested in, such as cameras and other computers and whatnot, which is a common source of noise even in the previous generation designs. So simultaneous recording is great. In order to evaluate how the broad cortical access performed, I did a dry fit of the entire fixture with the probes attached to it and lowered it to the extremes in the chamber it could go without potentially breaking a probe or bending a probe. When doing that, I was able to draw sort of a circle of the extremes that could be hit, with the assumption that everything in the center of those extremes can also be hit. When doing that, I found there was a 10 millimeter range that could be hit with these probes. And so the broad cortical access that had been lost in the 2nd generation was now restored with this design. Additionally, since there was still a lot of built-in space left, the multimodal integration was also enabled, since there was also still room for optic fibers to be implanted. So from this first attempt of design of 3 probes at once, I was able to learn that the single drive design is what is needed for sort of any future designs. as it's able to insert multiple probes at once without sort of any risks of limiting the insertion locations or having unstable, crooked insertions. By having physical barriers between the probes, that got rid of all of the crosstalk issues and was able to keep sort of some cable management. One lesson that was learned was that within the plastic designs that had worked so well initially, when actually putting it into metal, there's a lot of different properties. And in order to keep parts sort of well contained on there, there had to be some post-manufacturing modification. So any future uses of this design would need to be modified if they are going to be made in metal. And finally, there's some certain locations that cannot be reached with all three probes loaded on there. For example, in this edge case, two probes can hit sort of that corner, but the second you add a third probe on, it'll hit the wall. And so that limits sort of the simultaneous recording capabilities and might limit experimenters' ability to hit edge targets that could be important within your cranial window. And so I wanted to design something that could accommodate this limitation. So using the benefits of the previous one, I wanted to have the single drive keep those physical barriers that had worked so well, but create a design that now enabled recording from as close to the edge as possible, where the three probe design was unable to reach. The design that I came up with was sort of a very modular design. There's two identical halves that hold three probes each. And there is a built-in spacer within there that holds optic fibers. Each half roughly holds probes in a triangular design. And so then when placed all together, there's 6 probes on there and then spots for optic fibers in the very center. When actually put all together, this is roughly the pattern the probes look like relative to each other. And they were loaded, of course, onto the single drive. When evaluating it, this is the pattern that the probes would take within a chamber. And it had sort of that broad cortical access and, of course, built-in multimodal integration with the built-in spots for the optic fibers. When evaluating the simultaneous recording capability, once again, noise was really mainly restricted to the 60 hertz multiples, so that same electronic noise we had seen before. So that was also a success. But repositionability was not great. Since this design was so large, it took up 10 millimeters all at once. There's not much space within the 20 millimeter chamber, which is even slightly smaller than 20 millimeters with that implanted grid. That really the only repositionability of this is to rotate it around to hit sort of these different edge targets. The fiber placement is fixed at assembly. So since there is really only one way everything goes in, probes or fiber optics are just in the center. And there's one position relative to each other where probes work. So there's no linear distribution of them like the top diagram, but rather this sort of double triangle position relative to each other. This could be easily addressed by maybe making it less than 6 probes, but having sort of that same triangular design and allow more modularity to better hit those edge targets without so much constraints. When working on these designs that have 3, 6 probes, I found that there was a huge risk of breaking multiple probes at once. So in the first generation, if your screwdriver slips, you break a single probe, and that's just $1,400 out the lab's pocket. But a single slip now breaks maybe 6 probes at once, and that is orders of magnitude more expensive for a lab. And it also maybe restricts you from using, oh, this is a good probe. It's a nice straight probe, well-grounded. Oh no, I broke it. I have to do all the soldering again. Additionally, by having these more complicated fixtures that have 3 different parts, a bunch of screws holding everything in place, it takes a long time to put it together. Historically, experiments were done by assembling the entire fixture at the beginning with the single probe, doing the experiment, and then disassembling it and putting the probes into safe storage. However, with these like 3 to 6 probe designs, that's going to take a lot of time out of an experimenter's day. So it'd be great if there was something to store the fixture between designs, as well as have something for that initial assembly that keeps you from breaking everything when first putting it together. I created a custom assembly jig. This is for the 3 probe design specifically. It works first, top quadrant part holds the part with 2 probes upright and securely so that you can use your nerve pixels and you don't run the risk of having slippery fingers and dropping everything at once. Once everything is loaded, it can be moved to the second jig in the design. Nerve pixels are, in this design, are held on by a screw that is very close to the tip of where so a single slip is very risky as it's very close there. So by creating a design that has a hole right near there that constrains the movement of, can securely attach your pixels on there where they don't come off with any sort of movement. It'd be bad if they came off during an experiment, as they would fall off or break. Is for the second part of the sort of 3 probe design that also allows you to secure your NeuroPixel on. That is secure, can be combined sort of in that original second jig. There's 4 screws that hold both halves together to make a complete fixture. There's also sort of a gap there at the edge where the probes stick out there and sort of your assembly. Once everything has been assembled, you have sort of 3 probe fixture that can be attached to a drive that is attached to the 4th jig. The drive is fully attached to the parts it needs to be then transferred to the animal. So once you have everything done outside of the vivarium, you have your whole fixture complete, you can just unscrew it from the 4th jig and take it back with you, and it can go straight onto the animal's chamber and attached with. Then, after use, within the booth where the animal experiments take place, I created a sort of 2-part storage and cleaning fixture box. The entire fixture can be screwed onto the bottom part that is attached to sort of the wall of the booth, and there's a hole in the middle so the probes won't hit anything. A removable cup can be put into the lower half of it that can have interchangeable liquids. So after experiments, probes need to be cleaned with Turgazyme, and then before experiments, they need to be sterilized with ethanol. So by having this removable cup, you can just keep everything in one place and just change out the cups. And then once you're done for the day and you've cleaned everything, there's a lid that can be put over the top that keeps any wandering hands from accidentally reaching in and brushing and then breaking your probes. When actually comparing how the assembly fixture performed, 2 naive users were tested to see how they compared to like sort of historical, more experienced users of the fixtures. User A started without the fixture, and then in their second attempt to use the fixture, they shortened both their time, but also the number of probes hypothetically broken. No real probes were used for this, otherwise a lot of probes would have been broken. So they went down a count of 4 between their 2 uses. For user B, they had started with the fixture their first time around and thus took longer time-wise than without the fixture, but the number of probes actually broken were 7 without the fixture and then just 3 with the fixture. And compared to historic, sort of more experienced users, this tracks, where without the fixture, 4 probes were broken, despite being experienced of like trying to keep your screwdriver in place. But with the fixture, none were broken. So sort of a summary of this one aim. I was able to successfully create a good 3-probe fixture that supports upwards of 3 probes from a single drive, but also can be adjusted. If you don't want to assemble the whole thing, you can just do 2 or even 1 if you really felt like that. And it was validated through dry fit and saline testing. A 6-probe design was also created to sort of address some of the limitations of the 3-probe design, and it had some promising results and had sort of dedicated fiber routing, but there's definitely some more work that can be done there to better optimize the design. And then, of course, finally, the assembly and storage aids were created to reduce the amount of breakage and cost to the lab. But after all this saline and dry fit testing was done, that's a great test for the fixtures themselves. Do they work? There's no noise. Can they actually reach everywhere in the chamber? But neuropixels themselves sort of have curves to them sometimes. Everything in life that's manufactured has tolerances to them. In mice, you can sort of see exactly where when you insert your probe, you can see exactly what brain region you recorded from. So after a recording session, you can sacrifice the animal and do histology on it. And you can get sort of example tracks like that, which tell you this data set that I collected came from exactly this place in 3D space within the brain. In primates, that's not as possible. There's no second chance. These animals take a long time to train up to get to working well on tasks, and it is much more expensive working with them. So if they were to be sacrificed every time you wanted to see where did my probe go, that's not possible. However, it's still important to know what brain region you recorded from so that you sort of have this metadata of properties and you can compare these different brain regions to each other. So a new method is needed to sort of study and quantify how probes can bend during insertion, and then also use that data to back calculate where within the brain you have inserted based off of where you hit from the surface. First, to study how the probes actually bend and being inserted into the brain, I created a custom setup that allows the drive that holds the entire fixture to be lowered into a phantom material. I wanted to create also a clear imaging window so that during insertion, you can see before insertion, here's how it looked, and now once it's within the material, here's how it looks maybe differently compared to it. The replaceable fixture location is also important so that later down the line, if there's any other designs that use the drive, they can also be tested within just sort of this one setup. When deciding on the material for the phantom testing, I first started with agarose, as my plan was to dye the neuropixels with some food dye before inserting them, so that I could visualize the tracks within the agarose and see exactly where probes had gone across multiple insertions. When testing it with just a single neuropixel, however, I found that after a single insertion, within a number of minutes, the dye had diffused so far that you couldn't see at all where the probe had gone. It was just one large blob. So I pivoted instead to ballistic gel, as ballistic gel also has very similar properties to the human brain, or macaque brains as well, in terms of texture and squishiness, but is not as easily dyed since it's not as water-based as agarose is. Despite using a number of different dyes that dyed every available surface within the lab, including myself, nothing would dye the ballistic gel. But when slicing around where the probe had been inserted, I was able to put it underneath a microscope with a ruler and sort of evaluate where the probe had been. So in this example, this was a single neuropixel inserted about 15 times in the same XY position, and was very clear to image in this case. So for all future track imaging, I used ballistic gel. And yeah, there's sort of a red line there that helps show where the track is if the screen is not the best. I then wanted to use it with the 3-probe design. However, once I started putting these probes next to each other, I started seeing a lot of curvature. When there's just a single probe, there's not much to compare it to, but as you start putting more of them together, you start seeing the curvature more. So the optimal designed length between these probes is 4.8 millimeters, but you can see sometimes it went down to as much as 4.36 millimeters of distance between probes. And when actually inserting it within the ballistic gel, they curved even more towards each other to the point where if I had gone any deeper within the gel, I think the probes could have touched each other. And so when actually looking at the tracks as well, there's a lot of width. You can see differences between probes. A neuropixel probe width is about 0.07 millimeters, but tracks of especially curved probes were upwards of 0.4 millimeters wide, which is almost 6 times as wide as the probe itself.
Quick, I apologize.
Yes.
Question. This is still like 15 insertions or
yes.
some number. So like in the middle one on the left, you kind of see like 4 lines. That's different tracks.
Yeah, it was still in the same location, but it kept bending so much.
So when you're doing the width, is that the width of the different tracks, or is the whole that side like?
Yeah, the width of the sort of the max.
But like
yeah,
like from one line to the other one, that's like.
Yes, yeah. So the max sort of location that it went.
And the right is one. No, that's viewing it from the other angle.
Yes. So if you have sort of three probes, you can both look at the tracks this way and also turn 90 degrees and see how in line they are the other way.
Yeah, but in that case, you don't really have a good understanding of. They're all kind of maybe varying in different ways. And you don't know if which one is if.
Yeah. I suspect though it's that center one, as it visually when during insertions, you could see it going the most. And yeah, so based off of this, there was sort of 3 probes that I had used during this specific imaging that one I would classify as very straight to the naked eye. One maybe didn't look as straight, had some slight curvature, but it was hard to tell. And then the middle one was the most curved. Holding it up, it looked like a warped piece of wood at like Home Depot or something. And so that's also shown by the trajectory. So the straightest one was the 0.1 track, which is very difficult even to see with underneath the microscope. And then the most curved one had the widest, most variable trajectories. And I suspect it also led to the 0.5 millimeter width in the other direction. I repeated this with the 6-probe design. And I only did actually 3 probes for this test as it was very hard to image with all 6 in the way. And I found it was very difficult to see the tracks on this, both because I had used relatively straight probes, but for this specific experiment, I had started to use a new batch of ballistic gel, and I believe the lack of extra contaminants in there made it more difficult to see where the probes had actually been. As in previous ones, there was a lot of extra hair and dirt, so where the probes had actually been, there was a clear track where there was no dirt, but when everything's nice and clean, it's difficult to see where the probes have been. But I was still able to, during insertion, see how the probes were behaving, and they performed sort of the same. Straight probes stayed straight and curved probes still curved. So it wasn't a matter of how the probes were placed relative to each other, but rather just the characteristics of the probe itself. However, in these experiments, the surface is very flat. It's just sort of a chunk of ballistic gel. Your brain is not entirely flat. There's some curvature to it. So I wanted to repeat these analyses, but sort of in a brain-shaped simulation. Initially, I poured ballistic gel into a mold and put it on one of the surgery simulators built in our lab. And when I went to go image it, it was once again kind of difficult to see where the probes had gone, especially compared to the single and triple probe designs. And so I opted to do an additional insertion where I cut out a chunk of sort of the brain-shaped insertion just to image it during when probes were actually put in there. And I found that when using sort of that same crooked setup from the same probes from the crooked setup from the 3-probe one, they were less curved during their insertion. And I suspect the reason I was unable to see tracks from 15 insertions initially within the brain was it is possible they were hitting the same location so precisely between insertions that there was just no tracks to actually see very well. My hypothesis for how this performs is that the curvature of the brain helps encourage probes sort of to hit the same location rather than them hitting a flat surface and being free to go sort of any which way. But now that I had sort of this phantom testing of how extreme probes could bend and sort of how far they could go, I wanted to combine it with sort of trajectory planning tools. So when I insert in this location on the surface of the brain, where am I actually hitting? Am I hitting premotor cortex, or is this actually now primary motor cortex? For mice, there's a bunch of options for this. Things like Pinpoint or NeuroPixel Trajectory Planner have been well built for mice and allow you to sort of plan out exactly and predict where in the brain you're going to hit. But there's nothing already built like that for primates. And so I wanted to build a tool that I call StereoPlan that works sort of in both directions for primates. Both, if I insert here, what brain regions will I pass through? And then in reverse, if I want to hit this region, where do I have to target on the surface of the brain to achieve that? Under the hood, it's built off of the NIMH macaque template, which is a population average to MRI across a whole bunch of adult rhesus macaques. This allows it to be more broadly generalizable, as there's always going to be subtle differences between primates, but since it's averaged, it captures most of the similarities. Built into this is the Charm Atlas, which is an entirely labeled up to 6 levels of granularity for each section of the brain. I built in a physical sort of recording chamber geometry, as all primate experiments are going to have a chamber geometry, and probes are assumed as sort of straight line trajectories with a modifiable tolerance. So if you know that you're going to have a curved probe that might go upwards of 0.5 millimeter curvature, you can put that in and it'll expand sort of the scope of maybe what regions, if it was curving that extreme, would it hit. In practice, it is used in a number of different ways. So if first you wanted to just within your chamber look all about what hit, you could do so by just clicking anywhere within the chamber and changing how deep you want to insert the probe. It can be changed to different locations, and you can see the MRI on the right shows both sort of a crosscut of where you inserted with how deep the probe went. And then the probe can be changed from the standard 10 millimeter to the longer 15 millimeter or even a custom length. At the bottom right corner is a description of what brain regions you have hit and at what depths along the probe they would have hit. However, generally there's some restrictions. So for example, within the lab, we have those grids, and you can't insert through where there's not a hole within the grid. And so I created a second sort of drop-down menu within this software. You can select what grid design you have and click positions and see for the specific grid location that I have put in my chamber. When I use this hole, I hit this brain region.
The grids can be rotated,
Yes.
right? So I'm assuming there's some way you can do the orientation. Can be rotated like on a per experiment basis, right?
I got you. The chamber. If you wanted to move everything about, I don't have the grids shown in this video, but you can as well. You can move it both in X, Y, and Z. So if you wanted to move all the way to the other side of the brain, or if you have a ginormous chamber, you can also do that. And then you can also change the tilt of it, the pitch, roll, and yaw of it. So whatever your chamber is, whatever your grid placement is there, you can also make custom grids. So by saying sort of what your grid design is, you can modify it on a per use basis. And then sort of the reverse functionality of this. So I want to hit a certain brain region. How do I, in order to hit this? So if I wanted to hit areas 3A and 3B without the grid, you can see sort of a heat map in general, but you can also select a grid, and then it also shows a heat map on there of what is the minimum depth you would need to go in this location to hit that brain region. The table on the right also lists out when having a chamber selected, it'll tell you what holes you need to target to hit that region. Without a chamber selected, it gives roughly like XY coordinates within the chamber of where you would need to target. And then finally, there is an export button that'll export both images that you saw in sort of both functions, as well as all the details. So the table that tells you what holes hit and how deep you would need to go, so that you could just export it and look at it at a later time. There's some limitations of this. So it does assume sort of straight lines with variable widths of what can be hit. So if there's a precise curvature happening within the brain, it's not predicting that. And it's built on currently a population average template. So if there's individual differences between animals, it doesn't really show that within the MRI. However, this is an easy fix in the future to allow uploads of individual subjects' MRIs and then sort of overlay roughly the population averaged charm atlas over the top of that. Additionally, there's no persistent session files. So if you move the chamber all about, close the application and reopen it, you'll have to redo all of that. So whatever parameters you used for that, hope you wrote them down. Otherwise, it might be difficult to hit exactly the same location. But in the future, a save load function would easily rectify this. This is also not a ground truth software. If it says hit hole 18 to hit premotor cortex, and you go there and you're like, it's not right. There is some built-in calculations that might not perfectly match what you are doing. So it needs to be cross-referenced against sort of electrophysiological landmarks, both firing pattern, or if you know there's sort of LFP signatures for a certain region, that also needs to be attached to it. But it helps give you a better generalizable idea of where you have gone or where you need to go. So sort of in summary of this, I created a new phantom tissue testing fixture that allowed us to evaluate the tolerances of probes as they were being inserted. It could also be used if you have a particular probe that you are unsure of how straight it might be or how good of a probe it is. You could use this setup to also test that and evaluate, do I really want to use this probe or do I want to look for a straighter probe for this experiment. And I also created Stereo Plan, which is the software I showed before. Bless you. That allows for guided sort of trajectory planning, both forward and inverse. And in general, as future directions, while the ballistic gel was somewhat successful, it was more successful than the agar tissue that I had used. Recent work has shown that a higher concentration agar phantom allows for better track visualization, even without dye. So it leaves really nice tracks underneath the light. So that would be a good direction to explore to see if that's even a better material than ballistic gel. And yeah, I would like to thank my lab for all their support through the years, especially my mentor, Ryan Canfield, who introduced me to NeuroPixels, and then I've been stuck ever since thinking about them. And for everyone in the lab supporting me, especially throughout this quarter when I had so many issues. And yeah, I would also like to thank my friends who have supported me throughout my undergrad and my master's and kept me entertained on weekends where I would have otherwise shut myself in. And I'd like to thank my family for also supporting me. I would have had a much tougher time during undergrad if I hadn't been financially supported, especially by my grandfather, Jeff. So if he's watching, thank you. And also all my family supporting me as well, encouraging me as I've been doing this. And thank you to my parents. They're beacons of light in my life. It's always been great to call them as I'm walking home from lab, being like, I don't know how to do this. I can't think through this. And my dad will listen to me complain on, and then he'll give me an idea, and then I'll give another idea. Neither of our ideas work, but eventually, somehow, I'll get there. And my mom, who's always been willing to drop everything and come support me if I have issues in my life. And of course, I can't forget the house beast who looks at me with blank eyes when I say anything if it's not related to food. And yeah, any questions?